this video, we'll be looking at the photoelectric effect. So what is the photoelectric effect? So the photoelectric effect. So if we have an electromagnetic wave, and this wave interacts with matter, and on this interaction with matter, an electron is released from this matter, this is the photoelectric effect. So, electromagnetic wave interacts with matter, causing an electron to be released. The photoelectric effect can be seen in the form of a photoelectric tube. So photoelectric tubes are where we have a semi-cylindrical shaped piece of metal, or a conductor, and an anode. So electromagnetic waves hit this semicircle shape, or semi-cylinder shape. They then reflect the electrons onto the anode. The anode and the tube are then connected to a circuit, and then we get the movement of electrons around this circuit. So, this is seen in things such as the automatic alarms that you get in shops. So when you walk through the door and you have a buzzer going off to tell you that you've walked in the door and the shop owner can come out. So this uses the photoelectric effect. Also, certain types of smoke alarms use the photoelectric effect. So what happens in both of these instances is that we have a electromagnetic wave, UV radiation generally in the shop instance, but I'm not too sure on the smoke alarm. But we have an electromagnetic wave, it hits this semi-cylindrical tube, and it then causes the electrons to move around the circuit. Once this source of light is broken, so in the smoke alarm, if smoke goes into it, it breaks the beam of light, or in the shop, you walk through the beam and it breaks it. This causes a drop in the current. So if there's a drop in the current, a relay is then attached to this and it flicks off when there's a drop in the current, causing the alarm to go off because it starts up another circuit. So this is how your shop doors and your smoke alarm works. So the electrons that come off of the semi-cylindrical tube have a kinetic energy because electrons have a mass and they're moving. We can calculate the maximum kinetic energy of these electrons. So the way we do this, if we set up a photoelectric circuit and we don't have a potential difference, all the emitted electrons from the certain frequency of the light we're showing onto the tube are going to go around and form a current. If we put in a potential difference into this circuit now, the required energy for the electrons to jump from the tube to the anode has increased. The lower energy level electrons, so the electrons with the lower kinetic energy, will no longer be able to make it across this gap. So only the higher energy electrons make it across. If we keep on increasing the potential difference until a point where we get zero current, if we get zero current, that means there's no electrons flowing. If we get the zero current, that means that the highest energy electrons are no longer moving across. If we back off the potential difference again, we get an increase in the current until a point where we get the maximum flow, where we have zero potential difference. So, we get our minimum energy electrons as well as our high energy electrons jumping across this gap when we have zero potential difference. If we increase the potential difference until we get zero current in the circuit, that means our high energy electrons no longer moving across. So this is a simple experiment we can set up that can help us determine the maximum kinetic energy of our electrons. The kinetic energy depends on the frequency of the light that's shining onto the tube, or the frequency of the electromagnetic wave. So now we're going to look into the properties of the photoelectric effect. So first of all, there is a minimum frequency. This minimum frequency is the minimum frequency required of the electromagnetic wave for the emission of electrons. So any frequency of the electromagnetic wave below this frequency doesn't cause an emission of electrons. Any frequency above this minimum frequency of the electromagnetic wave causes an emission of the electrons. The intensity of this light, or this magnetic wave, onto the surface does not increase the energy of the electrons. It only increases the amount of electrons. So, we don't get an increase in the kinetic energy of our electrons coming off of the surface if we increase the intensity of the light. We only get a higher current forming. So we get more electrons moving. So if our energy for our electromagnetic wave is above our threshold frequency, so our minimum frequency is called a threshold frequency. If our electromagnetic wave is above this, we get instantaneous emission of electrons, no matter how weak our light is. So we can have a weak source of light, but we still get the emission. But we get a reduction in the current forming. So, the current is directly proportional to the intensity of the light. Electrons in a photoelectric effect are emitted with a range of energy levels. So it starts off with a minimum and reaches up into its maximum. So we get a range between this. We can sort out these ranges using the sort of experiment design that I told you about before. So we get a range of energies of the electrons being emitted. So another thing we need to know about is the work function. The work function of a metal is the minimum energy required to remove an electron from its surface. So, the work function is the amount of work required to remove an electron. For copper, for example, we need 4.7 electron volts as a minimum to remove an electron from copper. Other metals have different work functions, and you can find that out in your book. We can calculate the work function, which we'll get into later on. Because the photoelectric effect doesn't fit into our model of the wave nature of light, we needed to have a particle explanation for what's happening. So, Albert Einstein assumed three things in his explanation. First of all, there's particles of light called photons. These photons have an energy, E is equal to hf. The intensity of the radiation is proportional to the number of photons crossing per unit area per unit time. So if we look at this, if I have a light, one light globe is 100 watts and the other one is 200 watts. If we look at the wave nature of light, both of these lights are going to have the same sort of waves, except for the 200 watt one is going to have a high amplitude on its waves. If we look at the particle measure of light, if we look at the number of photons coming out of the 100 watt globe compared to the 200, the 100 watt globe is going to have half the amount of photons. So this is where the particle measure of light is more useful than the wave. Also, when a photon hits an electron inside the atom of a element, we get total transfer of the energy from this photon to the electron. So it's obeying the conservation of energy here. So we get a transfer of the energy from the photon to the electron. We can't just have partial transfer, we have full transfer. If we look at a piece of copper, copper has the energy level diagram of this. So, the energy level diagram has areas where electrons exist. Electrons exist in this zone down here, which is below negative 4.7 electron volts in copper. Electrons cannot exist in between 0 and negative 4.7 electron volts in copper. but they can exist above. So they get emission if we go above our zero, and we have the electrons just sitting inside the atom down here. So for an electron to escape, we need to be giving it a minimum energy of 4.7 electron volts to move from negative 4.7 to 0. We can give it higher energy. So if we had our 4.7 here, our negative 4.7, and we gave it 5.7 electron volts of energy, it'd be escaping with 1 electron volt. So we have a minimum energy required for an electron to escape the atom, or emit from the atom. So our incoming photon must have this required energy. So it transfers all of its energy instantaneously to the electron to form the emission. If we have a minimum energy, this kind of says that we need to have a minimum frequency. If we look at the equation, E is equal to HF, we have a link between energy and frequency. We can find out the minimum frequency. So the minimum frequency to cause an emission of an electron from a copper atom is going to be 1.13 times 10 to the 15 Hertz. So this is our threshold frequency of copper. So the minimum frequency that can cause an emission of an electron. Each atom, or each metal atom, has a different threshold frequency, and they also have a different electron energy level diagram. So, if we have a photon, this photon has an energy of 4.7 electron volts, and it hits our copper atom. It's going to transfer all of its energy instantaneously to the electron of the copper, causing an electron emission. So it doesn't matter how intense the light is, as long as we have at least one photon moving, hitting this copper atom, causing an emission, we get the emission. So it doesn't matter on the intensity, we're still going to get emissions. But if we have a higher intensity, we get more emissions. So if I have my copper atom still, and I have my electron sitting at an energy level of negative 4.7, if I have a photon with energy level of 6 electron volts, and it collides with this electron, causing a transfer of energy, this electron now has to gain enough energy to overcome this barrier here. So it has to go past the 0. So it's got negative 4.7 when we start, our photon has 6, so we're going to have 1.3 electron volts left over. So the electron emitted from the atom is going to have 1.3 electron volts. So this is how much kinetic energy our electron has. So we can calculate the kinetic energy of our electrons based on knowing the work function, so which is the work function is the minimum energy level where electrons can exist under, and knowing the energy of our incoming photons. So the kinetic energy is going to be equal to the energy take away our work function. If energy is equal to HF, our kinetic energy is going to be equal to HF take away W. Now W can be calculated using the threshold frequency. So our kinetic energy of our light, or the kinetic energy of our electrons is going to be HF, where F is the frequency of the incoming photon, take away HF naught. So HF 0 is the threshold frequency, times by Planck's constant. So we can calculate our kinetic energy this way. So the key points from the video today. The photoelectric effect is where we have an incident electromagnetic wave on a piece of metal. This piece of metal then instantaneously emits an electron. This only happens at a certain frequency. So anything above this frequency. So this minimum frequency required to happen is called the threshold frequency. The threshold frequency is related to the work function. The work function is the minimum energy required to remove an electron. In explaining the photoelectric effect, Einstein had to use the idea of photons and the conservation of energy to explain. The kinetic energy, the maximum kinetic energy of an emitted electron is equal to the energy of our incident ray take away the work function. So, our maximum kinetic energy is equal to HF take away W. To see how we use this and to graph it, the LiveScribe PDFs are your way to go.